Hello, it's Keith here, and this is lesson 6 of the Photon series of my 68000 assembly programming tutorials. What's Photon? Well, it's this little Tron clone that you can see here. We are a little line. We have to try and get the enemy to collide with our trails, and if we do, then we win. Now, this isn't really a very impressive display of the Genesis's video capabilities. It is, however, an experiment in making a tile sprite-based system work as a pixel plotting-based system, and I think it works fairly well. So that's what we're really going to be looking at today, how to plot pixels or simulate the plotting of pixels on the Genesis's tile-based screen. And we're going to be looking at that in just a moment. Now, before we do that, I do just need to describe some of the functions of the game because we will see them in the code. Now, if I press a direction and hold it, we only change direction once. I have to press and release. The other thing is I have a boost mode. If I hold down the fire button, or one of the fire buttons rather, we will move faster for a brief period. And this is so we can catch up with the enemy and just make the game a bit more fun. So we're going to see both of those represented in the game itself. Now, the way we're simulating this bitmap screen on this system is we're basically filling the entire screen with consecutive tile numbers so that every tile on the screen is different. And then what we're doing is we're changing the bytes that make up that tile pattern data, and we're basically changing the individual pixels to be what the color we want to show. And then when we're reading back for the collision detection, we've got a point routine that's reading back, and that's detecting when we do what we just did and die. Okay, let's go over to the source code and take a look. Okay, if we just go to the top here. Now, of course, you can download all of the source code from my website. I do need to point that out, apparently, because people keep complaining that I only use screenshots on my website. You don't need to copy paste it. Go to the website and download it and save yourself some time. Okay, so we're going to go over the basics here. I've covered it a lot before. I apologize if you've seen the others, but I do these assuming you've not seen any of the others. So we're going to go over the same stuff that I'm quite bored of discussing. Anyway, the game itself uses up to 5 colours, the background colour and 4 others. We can use all of them on the Genesis because it's a 16 colour system, so yay for that. And then we're defining the screen size. Now, because it's a vector-based game, Photon can really work with any screen resolution. This system is using 320 by 224, so that's what we're defining here. I'm going to use all of that. We need a few bytes of memory for our game variables, and we're defining those here in the memory of the system. We've then got our generic header here. We've got this initialization here, and then we're turning on the screen, and we are just setting up the screen and defining the palette. Now, I'm not going to discuss these in detail. If you want to see them discussed, see the simple series or see the YQuest series. I've been over this so many times, I can't bear to do it again. So we're going to skip over that, and we're just going to go straight into the new stuff for Photon. Now, we're using this fill area with tiles routine, and this will take an area and it will fill it with consecutive tile numbers. And this was also taken from the simple series where we drew the Chibico character on the screen. This time, however, we're filling the entire screen with consecutive tiles, and we're starting from tile 1. We're leaving tile 0 blank because that will be used by sprites and things that have been uninitialized. So we're starting from 1. Tends to work a little bit better, so that's what we're doing there. And then we're resetting the game variables so that we've got a clean start state, and then we're showing the main menu here. Now, this is the main game loop, so this is what repeatedly runs during the gameplay. What we're doing here is we are incrementing the tick. The tick is either 0 or 1, and this relates to boost mode. In boost mode, when we're moving faster, we update the game every tick for the player. When the boost mode is off, we update the player's movements every other tick, so it speeds the player up by 100%. Now, we do have to have a delay here, and the delay is actually different when boost mode is on. That's not because we want to speed things up, it's because the drawing of the boost counter in the corner is a little bit slow, so we need to decrease our delay to compensate, so that's what we're doing here. We've got a buffer for key presses, and if then any keys are pressed, we update that buffer with the new key presses. Now, this is a little bit interesting because on the other systems, I was checking the key presses, and if nothing was pressed here, I was clearing the key timeout, which is how we detect if the key's been released so that we know we want to move again next time. That wasn't working for this system within this inner loop. I had to move it to the outer loop here. I think the problem is it's what's known as debouncing on electrical switches. If you press a switch down, it doesn't go from 0, you press it down and it goes constantly 1. It will flicker off and back on again briefly, so you need to sort of average it out a little bit, I think, and that seems to have been the problem here. I've not come across this on any of the other systems I had to work with, but this one, it was detecting that the button had been released when it hadn't. I don't know. Anyway, I had to change it and it works now, so I'm happy. That's all. It's all I needed was it to work. I don't have to understand quite what the problem was, but anyway, as I say, Did have to make a change there. Now here is the start of our main loop, and what we're doing here is we're checking if the key timeout is clear. If the key timeout is not clear, the player never released that key, and we don't want to process any more directions, because if we did, the player would just circle around instantly and collide into themselves, which would be a bit of a shame. So we're skipping over if the key timeout is set still. If it's not, we're going to update based on the player's directions. The first thing we're doing is we're turning boost mode off by writing a 1 to the boost variable. Then what we're doing is we're loading the player direction into A3 and the player X acceleration into A6. Why are we doing this? Well, if the player turns left or right, we're going to need to increase or decrease the player direction. This goes from 0 to 3, representing north, south, east, west type 90-degree directions. And if the player has turned, we need to update the accelerations, which are added to the player's position every tick. Now, we're now checking the two joystick bits for left and right, and we're decreasing or increasing the player direction in A3 accordingly. And then we run set player direction, which updates the X acceleration and Y acceleration, which is the bytes after X acceleration, accordingly. So that set player direction handles all of that. And then we're setting the key timeout so that no more key presses will be processed until the key is released again. Here's where we're checking the fire button. If the fire button is pressed, we check if there's boost power. If there is boost power, then we turn the boost power on by clearing the boost variable here, and that will turn it on. The actual processing of the boosting and all of the collision detection and all the drawing and things is handled by these multi-platform routines here. And then we jump back to the top of the main loop here for the next tick. So that's very similar to the code we've seen in the past, quite boring. The interesting bit, at least as far as I'm concerned, is the PSET and the POINT routines. Now these are basically going to calculate a tile on the screen based on an X and Y pixel coordinate. We're then going to work out which line within that tile we need to change, and we're going to change one of the pixels within that line. Now on this system, each pixel uses a single nibble of data, so we're going to have to change 4 consecutive bits to change the pixel. But we're going to load in the entire line of the tile. The line of the tile is 8 pixels, so that's 4 bytes, 1 long on this system. So we're going to load in the long, and we're going to alter one of the nibbles accordingly. We have a function called calc vram address, which will calculate the memory address of the long we want to change, containing a total of 8 pixels. We're then going to define that we want to read from that, read in the current data. We're then going to define we want to write to that. We're then going to calculate some masks to alter the pixel. And what we're going to do basically is we've got some masks, you can see them here. These are the masks for the nibbles. As I say, there's 8 pixels in each long. So these are the masks for the 8 pixels, the 4 bits that make up that pixel's color. And then we've got masks for the colors. So this is a mask with all of the pixels set to 0. This is a mask for all of the pixels set to color 15, and so on and so forth. Now, if we mask these two together, we will get the pixel we want to change in the color we want to set it to. And that's what we're going to be doing. So we use calc vram address, which we'll have a look at in a moment. And then we read in our byte. And then what we're doing here is we're getting the mask for the pixel we want to change. Now, each long contains 8 pixels. So we're taking the bottom 3 bits of our X coordinate here, and we are using those to select the correct masks from that mask you saw just here. So that will be the position within that long that we've read that we need to change. What we're doing here is we're storing that in D1. That's a mask for the pixel we want to change. We're then flipping the bits, and that's the mask for the other pixels within that long that we don't want to change, that we want to leave the same. Okay, now what we're doing next is we are getting the color, which is passed in D2, and we are calculating the mask for that color, which is going to be one of these. We take that mask for the color, we calculate the address of that, we then mask that with the pixel that we want to change, and that has now set the pixel we want to change in the color we want to change it to. We've now got that. What we do next is we add the background mask, just that we'd set just here, with the pixel we read in from the screen. That removes the pixel we want to change. We then all in the new pixel, in the color we want to set it to, and we write that back to the screen. And that has set one of the pixels within the pattern line to the correct color without changing the other ones. And so we've changed that one pixel's color. Now, a lot of the work of that has been done by this calc vram address function. Now what this has to do is it has to work out the tile and the line within the tile that we want to change, and that's what it's doing here. So we're ignoring the bottom 3 bits of the X position here because those are one of the pixels within the long that we're processing later. So we're only looking at the top 5 bits here of the X position, and we're effectively multiplying them by 8 times 4. Why 8 times 4? Well, there's 4 bytes per line and there's 8 lines per tile. So we're effectively calculating the horizontal tile position of the X position that we've been specified. So we're doing that here. We're taking those bits there. We're left shifting it to the left twice, which is effectively doing that multiplication. And that's the first part of our calculation. Now we're taking the bottom 3 bits of the Y position. The bottom 3 bits will be 0 to 7, and that's because there are 8 lines within each tile. Now each of those lines is 4 bytes, so we're taking that Y position and we're multiplying that effectively by 4 by doing 2 shifts to the left here, and we're then adding that to our previous calculation. Now that's calculated the Y position within the tile, but it hasn't calculated the tile strip position because there's going to be an extra calculation we need to do there. So to calculate which strip of tiles we are in for the current Y coordinate we want to look at, we need to take the remaining 5 bits of the Y coordinate and multiply them by 40 times 8 times 4. Why that? Well, because there's 4 bytes per line, 8 lines per tile, and there's 40 tiles per horizontal strip. And that's what we're looking at with these top 5 bits. So we're going to do that calculation, and we do it in 2 parts because we can't multiply by 40 particularly easily. So we bit shift to the position representing multiplying by 32, add that, and then bit shift to the position representing a multiplication times 8, and we add that again. Now the final thing we do is we add 32 because we didn't use tile 0. We started from tile 1 with the tile map that we drew onto the screen. So we're adding 32 to skip tile 0. The pattern definitions are start at memory address 0, so we don't need to add any kind of pattern definition base. So that's all fine. We've now calculated the video RAM address of the tile that we need to change on the line within the tile, and it's only the remaining X position from 0 to 7 that we need to calculate, which of course we did with the pixel mask. Now the next thing we need to look at is this read and write function. Now we're just going to briefly go over these. Basically we take a memory address as a word, and we have to shift the bits around to work with the rather crazy format that the Genesis uses. And I'm pretty certain the reason it uses such a crazy format is because they were maintaining backwards compatibility with the Sega Master System, which had a lot less VRAM, so didn't think about having much higher memory addresses. So we just need to shift these bits around a little bit. The other thing we need to do is, if we are writing to VRAM, we need to set this bit here, the second bit from the top. That defines it as a writing address. If that's a 0, it's a reading address, and that's why we've got 2 versions here. This version is the writing version, this version is the reading version. Apart from that, they're basically the same. So that's what we're doing. The final things we've got here is the fill area with tiles routine. That just writes consecutive tile numbers to the tile map. I'm not going to cover that. I've covered it before in the simple series. We've got the joystick reading routine here. I'm not going to cover that. I covered that in the YQuest series and the simple series. I've done it far too many times. The rest's all pretty much the same as stuff we've seen before. So there we go. I quite enjoyed doing this. I did get some satisfaction making these systems that are designed to be tile sprite systems, draw some pixel plotting, because I do prefer bitmap screens, although I in no way am pretending that this is going to be an efficient way of working with this system, but I did find it fun to make it do it all the same. As I say, you can go to my website, you can download the source code for today's example, you can also download the build scripts, so hopefully you can build it yourself as well. And as I always say, you're welcome to mess with it in any way you like, and if you manage to make something far better, you don't need to give me credit, you can take all the credit from that, because I'm sure you deserve it. Anyway, I hope you've enjoyed this. If you have, please hit the like button, because if you like the videos, YouTube recommends them more, and if you would also hit the subscribe button, then I'm sure I'll be doing more Genesis in the future, so maybe you'll get to see something you'll enjoy. Anyway, thanks for watching today. If you've enjoyed this video today, please consider supporting my content. It takes 20 to 30 hours a week to keep making these videos. It's basically all I do when I'm not doing my day job, and it's only through the support of my patrons and the other sponsors that I'm able to continue justify doing it, essentially. You can back me on Patreon. I post a weekly update with the latest work on the current projects I'm doing. You can see one here, and also the newest videos. There's a large backlog of videos that are currently only available to the patrons, although they will all be available to everyone later on. And also it's the backers who I ask when it comes to making decisions on how to change the content in the future, what new content to create and things like that. You can see there was recently a survey of the backers so I can plan next year's content. As well as Patreon, you can now become a member of my channel on YouTube. There's a join button you should see just below this video. You can use that. YouTube backers get the same content as Patreon. I just post it through the YouTube interface instead of the Patreon one. It's the same content every week. Also, if you prefer, you can go to my Teespring store and you can get some Chibi Akuma's merchandise or some Learn ASM merchandise if you prefer, if that's how you would like to back me. Links for all three are in the description of this video below. Anyway, whatever you decide to do, I hope you've really enjoyed this video. Thanks for watching today, and goodbye.